What if I told you your CPU has like 16 cores sitting there doing absolutely nothing while your graph traversal is taking 3 seconds? We're fixing that today. We're going full parallel, we're going full openmp, and we're going full unhinged. Okay, so today we're implementing parallel depth first search and breadth first search using openmp in C++. If you don't know what openmp is, it's basically the hash pragma annotation that tells your compiler to get the homies involved. Homies being threads, obviously. Before we write anything, let's talk about why sequential graph traversal is mid as hell. So here's your standard DFS. One stack, one thread, one core. You push source, you pop, you visit, you push neighbors in the reverse order so the leftmost child gets processed first. Because stacks are LIFO and we are not psychopaths. We iterate the neighbors in reverse, so the first neighbor ends up on top of the stack. It's like loading a dishwasher. Order matters, even if it looks chaotic. This works, this is correct. But on a graph with a million nodes, this is running on one core while the other 15 are literally watching Netflix. Alright, parallel DFS. The core idea is instead of one guy doing all the work, we give each thread its own local stack and a shared global pool for when threads run out of work. Think of it like a restaurant kitchen. Each chef has their own prep station, that's the local stack. But there's only one shared pantry. The shared pantry is the global pool. When a chef runs out of ingredients, they go and grab more from the pantry. The visited array uses atomics. This is critical. If two threads try to claim the same node simultaneously, we need a race condition proof way to say this node is mine. That's what compare exchange strong does. Okay, let me explain compare exchange strong because this is the real sigma move of the whole program. CAS, compare and swap, is a single atomic CPU instruction. It says if this value is what I expect it to be, swap it to the new value. Otherwise, tell me that you failed. There are no locks, no mutexes, and no waiting in line. In our case, expected equals false. So we say, hey, visited node, are you false? Okay, if you are cool, set yourself to true because you're mine now. If another thread already claimed it, expected gets updated to true, and we just move on, zero drama. Ends. It makes sure the CPU doesn't reorder these operations across threads because CPUs are sneaky and will absolutely reorder instructions if you let them. So you don't want that. This pragma spawns our thread team. Everything inside this block runs on all threads simultaneously. Shared means these variables are seen by everyone. They live in the same memory. Local variables like local st are per thread automatically. When a thread's local stack is empty, it goes into the critical section to steal work from the global pool. We steal in batches of 64, not one at a time, because entering a critical section has overhead. So batching is a W. It helps us optimize performance. This part is low-key the hardest part to get right. When should we stop? We stop only when both the local stack and the global pool are empty. If the pool still has nodes, we continue spinning. Another thread might donate more work soon. This is basically the distributed systems equivalent of are we there yet? No. Are we there yet? No. Are we there? Yes. So we continue spinning until we are. Work donation, the clever bit. Type the processing node plus newly claimed plus donation logic. This is the chef's kiss part. When a thread discovers multiple unvisited neighbors, it keeps one for its own local stack so it stays busy, and it donates the rest to the global pool for the other threads to pick up. It's load balancing without a load balancer. The algorithm self regulates. Threads that finish early get fed by threads that find lots of neighbors. Absolute beauty. At the end, we just concatenate all per thread result vectors. The order is not the same as sequential DFS, it's interleaved per thread, but the set of visited nodes is identical. We verified this in the benchmark. Moving on to sequential BFS. Sequential BFS, quick recap. It's queue based, it's level by level. Level of I stores BFS depth from source, and -1 means unreachable. There's standard stuff, nothing to see here, so you'll just swiftly move on. Now, the interesting question is, how do you parallelize this? BFS was stack based, so threads could have their own stacks. BFS is level based, so we need a different trick. We can't directly assign all of this to threads. Parallel BFS uses a frontier based approach. A frontier is just the set of nodes at the current BFS level. We process all the nodes in the frontier in parallel to find the next frontier. We process all the nodes in the frontier in parallel to find the next frontier. Think of BFS like a ripple in water. Each level is a ring of the ripple. We can process every node in a ring simultaneously. They don't depend on each other. That's our parallelism. Pragma OMP for basically distributes the frontier nodes across the threads. No wait means the threads don't have to synchronize at the end of the for loop. They go straight into accumulating into the local next. That is the local next to next frontier wala section. Again, over here, CAS saves us from the race conditions on level of neighbor. Only the first thread to claim a node gets set to its level. Everyone else sees a non -1 value and moves on. Now let's talk about the benchmark setup. We generate random graphs using the Mersenne twister. That's MT19937. It's actually really way better than the random. Random is like the 2009 Honda Civics of RNGs. RNGs is a random number generator, and MT19937 is like the 2024 BMW M3. So it's basically a glow up. We test three graph sizes: 100,000 nodes with average degree 10, 500,000 nodes with degree 15, and 1 million nodes with degree 20. So that's a small medium, and I hope you have RAM configs. The benchmark function is a clean little template that wraps any callable, times it, and returns the result plus duration. The chrono scope resolution high resolution clock gives us nanosecond precision because milliseconds alone aren't dramatic enough. Correctness check. We sort both the sequential and parallel results and compare them. The order will differ. Parallel is non-deterministic, but every node that sequential visits, parallel must also visit. If this says fail, you have a bug. Touch grass and debug. Compile with the fopenmp flag. That's what enables the openmp. Also use -O3 for the optimization. Parallel BFS, especially that frontier parallelism, is clean. The DFS speedup is a bit more variable because of the critical section overhead on the global pool. That's the bottleneck. The critical section is what is the major bottleneck. The more cores you have, the better. On 8 plus cores, this scales really nicely. On 2 cores, you'll still have a speed up, but you'll be like, okay, bestie, effort appreciated. And that's it. Parallel DFS and BFS using OpenMP, atomics for lock-free node claiming, work stealing for load balancing, frontier parallelism for BFS, the full stack no cap. If this video helped you understand either OpenMP or graph traversal better, drop a like.